You step into a small metal box. The doors slide shut, locking you inside. You are suspended hundreds of feet in the air. Suddenly, the lights flicker and die. It's a primal nightmare, yet modern cities depend on this exact technology to function. Without the elevator, the high-rise buildings that define our skylines would be impossible to use. Despite our instinctual fear of falling, this dangling metal box is statistically one of the safest ways to travel ever engineered. So what happens if the main steel cables suddenly snap? What hidden mechanical systems step in to prevent a catastrophic freefall? To understand why we are safe, we have to look past the cabin walls and uncover the engineering hidden deep inside the concrete shaft. This is a standard traction elevator. Strip away the building, and the system consists of a motor at the top, a passenger cabin, and heavy-duty steel ropes connecting them. Passenger cabins are never suspended by a single thread. In reality, they are held by a bundle of resilient, independent steel cables. If one snaps, the remaining ropes easily carry the load. The system uses a counterweight. This heavy block sits on the opposite end of the ropes, balancing a half-loaded cabin. Because it's balanced, the motor only expends the energy required to move the weight difference between the two sides. Managing these loads requires industrial-scale hardware, specifically massive grooved pulley wheels, greased mechanical joints, and thick steel ropes routed through a dedicated machine room. This balancing act makes the system incredibly energy efficient, but it doesn't solve the ultimate fear, a complete severance of every suspension rope. Let's look at the scenario where every primary steel rope snaps at once and gravity takes hold. Notice this thinner cable running parallel to the main ropes. This is part of the governor, a secondary mechanical loop that monitors the elevator's speed. As the cabin drops, it spins the governor's tension wheel. Centrifugal force swings metal flyweights outward, locking the wheel dead. The cabin jerks against this now fixed rope, which pulls a mechanical lever on its side. This lever pushes metallic wedges into the vertical guide rails. By using the cabin's own downward momentum to drive the wedges tighter, the system physically jams the elevator in place. This mechanism operates entirely on physical force. It requires no electricity or software, providing a reliable safety layer that has protected passengers for decades. An elevator cannot fall because the governor weaponizes the laws of physics, gravity, and momentum to trigger its own emergency brakes. While total cable failure is extremely rare, power outages are much more common. Most modern lifts include an automatic rescue device, or ARD. During a blackout, its independent battery backup takes over to deliver passengers to the nearest floor and open the doors. Even at the limits of the shaft, physical fail-safes are waiting. There is a safety clearance at the top called the overhead, and shock-absorbing buffers installed in the pit below. These systems rely on civil engineering for success. A safe lift requires a perfectly vertical, waterproof concrete shaft built with absolute accuracy. Looking ahead, we're seeing the integration of AI traffic control and even ropeless elevators that move via magnetic levitation. However, these complex electrical systems make elevators dangerous during a fire. Because of the risk of smoke entry and power failure, stairs remain the only safe exit in an emergency. The modern elevator is an impregnable fortress of overlapping engineering disciplines. It is a system specifically designed to conquer our fear of the heights through layers